Welcome to the Deep Dive. Today we're exploring a really fascinating concept from geometry, Jacobi fields. Our mission is to understand how these mathematical objects, well, how they describe more than just the shortest path in curved space. They tell us about stability, about how paths behave near each other.
That's a great way to put it. You know, in Riemannian geometry, we always start with geodesics. Those are our straight lines. But Jacobi fields, named after Carl Jacobi, they give us the tools to measure how these geodesics spread apart or come together. It's all about the curvature of the space itself.
Okay, so let's dig into that. What exactly is a Jacobi field? If I have one geodesic, what is this associated field measuring?
Right. So imagine your geodesic, let's call it gamma. A Jacobi field, J, along gamma, essentially tracks the difference, the tiny separation between gamma and another geodesic that starts infinitesimally close by. You can think of it as arising from a whole smooth family of geodesics. The Jacobi field is basically the velocity vector of that family moving away from the original geodesic. It's the tangent vector in the space of geodesics.
Ah, I see. So it's capturing that initial wobble or deviation.
Yeah.
But you mentioned curvature. How does the space itself control this deviation? That's where the Jacobi equation comes in, right?
Precisely. And this is where it gets really fundamental. A vector field J is a Jacobi field if and only if it satisfies a specific differential equation. It's a second-order ODE. And the key thing is that it directly involves the covariant derivative, D, and crucially, the Riemann curvature tensor, R.
The curvature tensor R. So that term Rj, gamma dot in the equation,
Yeah.
what's it actually doing to the Jacobi field J?
It's acting like a force, you could say. R measures the intrinsic curvature. If the curvature is positive, like on a sphere, this term tends to pull J back, making nearby geodesics converge. If the curvature is negative, like on a saddle surface, it pushes J outwards, making geodesics diverge, often exponentially. So the equation fundamentally links curvature to the behavior of nearby paths.
Okay, let's make this more concrete. The sources often use the unit sphere as the go-to example. On a sphere, geodesics are great circles, like lines of longitude. If you start two paths very close together at the North Pole, heading south.
They initially spread out, right? The distance between them increases.
Exactly. But then, inevitably, they meet again at the South Pole.
Right. And that meeting point, the South Pole in this case, is what we call a conjugate point. The amazing thing is that the Jacobi field tells us this is going to happen. Along that great circle segment from North to South Pole, the magnitude of the Jacobi field behaves like, well, like Sint, if the dis. The distance traveled. So at the North Pole, T0, the field is 0 because the paths start together. It grows, peaks at the equator, and then shrinks back to 0 precisely at the South Pole, TPA.
So the field vanishing, GT pi, equals 0, 0, that detects the intersection.
It is the detection. The vanishing of a non-trivial Jacobi field signals a conjugate point. It's the mathematical signature that paths which started parallel are forced by curvature to cross again. And this works on any Riemannian manifold, not just the sphere.
That's powerful. So the equation lets us predict these conjugate points, these potential points of instability or refocusing, without actually tracing out all the neighboring paths.
Yes, exactly. And because the Jacobi equation is a linear second-order ODE, its solutions behave nicely. Given the initial value J0 and its initial derivative ddt J0, the solution JT is unique. This structure leads to another key property. All the possible Jacobi fields along a single geodesic form a vector space, and its dimension is always twice the dimension of the manifold itself. For a surface, it's 4D. For 3D space, it's 6D.
Interesting. And I recall that sources mentioning trivial fields, like the tangent vector itself, and in flat space, the fields are just linear.
That's right. The tangent vector dot gamma t is always a Jacobi field, representing just sliding along the same geodesic, and dt tan dot gamma t represents a uniform reparameterization. In flat Euclidean space, where R0 the equation simplifies drastically and the solutions are just jt, a plus bt, simple linear motion reflecting parallel lines staying parallel.
Okay, pulling this together then. What's the big takeaway for you, the listener? Jacobi fields seem to be this crucial link between the abstract geometry of curvature and the actual behavior of paths moving through that geometry.
Absolutely. They are the fundamental tool for analyzing the local stability of geodesics. Do nearby paths stay nearby, or do they fly apart or refocus? The Jacobi field answers that. And connecting it further, finding where Jacobi fields vanish, finding conjugate points, is deeply related to things like geodesic completeness, the existence of shortest paths, and even in general relativity, how gravity, through space-time curvature, focuses or defocuses bundles of light rays or particle paths.
So here's something for you to think about. We saw that on a sphere, A vanishing Jacobi field signals a predictable crossing point, the South Pole. But what about spaces with negative curvature, where geodesics tend to diverge exponentially? How might a Jacobi field that grows very rapidly, never vanishing, relate to concepts like chaos or the extreme sensitivity to initial conditions we see in some physical systems? That's definitely something worth exploring further. This has been The Deep Dive. This deep dive was created by Mike Bro and is sponsored by embersilk.com.